Hello everyone. In the last session, we have discussed about some of the basic concepts related to semiconductor material. And in this session, we will be discussing about the basics of semiconductor diode. Okay? So, first of all, okay, a diode is basically a semiconducting device that allows current to flow in one direction. Okay, and this is basically a symbol of a typical p-n junction diode. Fine, and this here represents its image, and this is nothing but the internal structure. Okay, as we can see here, we have the p side and here we have the n side. So basically, p-type semiconductor here is fused to a n-type semiconductor to obtain a p-n junction diode. Okay, what exactly are p and n-type semiconductors? That particular topic was already covered in the previous session. So at first, let us consider p and n region being fused together without applying any external bias. Okay, so first of all, we know that p region consists of holes or vacancies. Okay, and n region consists of excess electrons. Okay, when merged together, okay, the electrons here have a tendency to move towards p side, resulting in the creation of immobile ions in the junction. That is because electrons here, they occupy the electrons which are present here, they try to occupy the vacancy, okay, in the other section. Okay, this basically forms a barrier, okay, between the two sides, and this region is actually called as depletion region because they are depleted from any free charge carriers. Okay, and basically this whatever depletion region is there or barrier is there, it basically creates an electric field here, okay, that will prevent any more flow of electrons from n to p side. Okay, one thing we should consider here is that even though the majority carriers here are the holes, and the majority carriers here are the electrons, as it was shown in the previous image, we have minority carriers, okay, in each section. Okay, when an electric field is created in this region, the minority carriers present in this section tend to move towards the other side. Okay, so that results in drift current. Okay, and along with that, very few majority carriers also cross the border. Okay, that is called as diffusion, and it is called diffusion current, and it is caused due to concentration gradient. Okay, but one thing we should know is this drift current and the diffusion current, which are present in this particular interval or during this operation, actually cancel out each other and equal to 0. So that is about this particular slide. In this slide, we'll be learning about biasing a diode. Okay, so first of all, what exactly do we mean by biasing? Biasing means applying this external fixed DC voltage or current, okay, across the diode, and we do this in two ways. One is called as forward bias, and one more is known as reverse bias. As we have noted in the previous slide, this indicates the p side, this part, and this indicates the n side. Okay, so p is connected to positive terminal, n is connected to negative terminal. So this gives the forward biased condition of a diode. Okay, and resistors are used in the circuit to prevent any excess flow of current and all, and to basically protect the circuit. So right now we'll not discuss more about that. We'll only focus on the diode and the applied voltage. So what happens here is, already we know that in this particular circuit, okay, there is an electric field created. Okay, so here there is an inbuilt electric field, and here there is externally applied electric field. So when there is externally applied electric field and inbuilt electric field in the circuit, what happens is effective electric field, at the junction, so this is this here, that reduces. Okay, so what happens here is electrons in N, okay, and holes in P are pushed towards the junction. Why are they pushed towards the junction? So actually here what we have is, here it's the positive side, so we can consider that here we have positive and here we have negative. Okay, so this electrons repel the negative terminal. Okay, and and so what happens is they are pushed towards the center of the diode, that is the junction, and same thing applies on the other end. Okay, so what happens is the junction width reduces. Okay, and basically, as you know, the depletion region extends. Okay, resistance offered by diode increases, but because it became more narrow, or because the width reduced, the resistance offered by the depletion region also reduces. Okay, but until the applied voltage is less than the barrier potential. Actually, if we consider the element here as silicon, okay, or the semiconductor considered here as silicon, which is doped with some trivalent and pentavalent impurity, then its barrier potential is around 0.7. Okay, for germanium it is 0.3, and it keeps changing per what semiconductor you take. So if it is silicon, the barrier potential is 0.7 volt. So until the applied voltage here exceeds this voltage or equal to this voltage, the amount of current flow is very less. Okay, but once it exceeds this, a large amount of current starts to flow, because large amount of electrons here starts to flow towards the positive terminal. Okay, so what it does is it reaches this part, okay, and then from here it goes to positive terminal. Okay, so this is how the circuit is supposed to be. Okay, so this is the direction of electron. Okay, and the conventional current direction, this is of electron, and conventional current direction is opposite to that. It occurs in this direction. This is how current flows. Okay, and we can call it as a switch, a closed switch. So in short, diode conducts. So as we increase the bias voltage, more and more electrons and holes cross the junction and current increases. Okay, so that was about forward bias. Next we'll be seeing reverse bias. So as we can see here the P side is connected to negative terminal and N side is connected to positive terminal. Okay, so this is the initial unbiased state, how exactly it will be. Once it is connected to this particular voltage, we'll see what exactly happens. Okay, so as we can see here, P is connected to N and N is connected to positive. So what happens is, it's something like this. Here let us assume it is minus, here it is plus. See, here we have electrons and here there is positive terminal. Obviously it will get attracted to positive terminal, so it will move away from the junction. Okay, and okay, when that happens, as we can see here, the depletion region widens. Okay, and obviously the effective or the resistance offered by depletion region also increases. Okay, but one thing we should consider here is, here for example we have electrons, and similarly here we'll be having holes. These are the minority carriers. They actually cross the junction. Okay, and then as we know, here it is minus, here it is plus. What happens is, these electrons cross the junction and reach the positive terminal, just completing the circuit, or causing current flow in the circuit, but their magnitude is very less. Okay, it could be in micro, or with recent technology it could be in nanoamps. Okay, and this particular current is known as reverse saturation current. Okay, and it does not change with the applied voltage. Okay, and but one thing is, when temperature increases, thermally generated minority carriers will increase. That will cause increase in the current flow. There is an important point to note here, that with every 10-degree increase in temperature, saturation current or reverse saturation current doubles. Okay, so and again, okay, there is one condition that we should know. There is something called as maximum reverse voltage. Okay, that is the maximum voltage that can be applied, beyond which breakdown occurs. That is, large amount of minority carriers will try to cross, they'll appear at the depletion region, and conduction occurs very heavily, causing causing the breakdown, or that could basically damage the diode. Okay, this is nothing but the VI characteristic, or basically IV characteristic, that is the current versus voltage plot. Fine. So here, as we already know, initially, now this actually represents the forward bias condition, and this represents the reverse bias condition. So if we see here, initially the current is very low when certain knee voltage is attained. That is, for example, let us assume it is 0.7 volt or something. So current increases. Okay, on the other hand, initially the this current is actually due to minority carriers. Okay, and when breakdown occurs, when reverse breakdown voltage is applied, lot of current starts to flow. Okay, damaging the device. So one thing we should know is that the positive sign that we represent here, the holes, are nothing but vacancies. Okay, and holes are actually not the ones which move, it's the electrons which move and occupy them. Okay, so that is one thing that we should be very clear in this particular point. So next we'll be speaking about the resistance levels. So when we speak about diode, three important resistance concept will come here. One is known as DC resistance, then we have AC or dynamic resistance, average AC resistance. Okay, so actually all these resistances, they depend upon the applied input signal. Okay, so first of all, what we have is DC resistance. DC resistance simply means that we have applied voltage in DC. Okay, and the resistance offered is known as DC resistance. That is, if the applied signal is nothing but DC signal. So similarly, when an AC voltage is applied, in that particular case we obtain AC or dynamic resistance. Okay, so we'll see about average AC resistance later on. First we'll see how exactly we'll obtain DC resistance. Okay, to obtain DC resistance, we need operating voltage and current. Okay, let us consider some particular point here. Okay, this will correspond to some current and some voltage. Let us assume that the current is basically 10 milliamps and the voltage is 0.9 volt. So this is nothing but the operating condition, that is the operating voltage and the operating current. In short, we are conducting the diode, or we are operating the diode in this voltage and this current. Okay, then resistance RD or DC resistance will be obtained just by dividing the given voltage with current. Okay, that is 0.9 by 10 milliamps. Okay, that will give you DC resistance. Okay, and next, coming to the next point, but one thing we should know here is here, okay, as you know, we go to the right side. Okay, now this curve, it extends, it doesn't stop over here. Current increases with increase in voltage. What happens is resistance offered here will reduce as we move to the right side. Okay, so now here, if we consider this particular diagram, we already know that this section represents forward biased condition and this reverse biased condition. So when the diode is in the forward biased state, the resistance we get is called as DC forward resistance, and in the reverse biased state it is called as DC reverse resistance. Okay, so DC forward resistance and DC reverse resistance. Okay, case of AC or dynamic resistance, this Q point keeps on moving up and down. Okay, that can be explained using this particular diagram. That is, initially, like, because the applied input is AC, initially its value could be in 0, then some VD max, then it reduces to 0, VD minimum, and then 0, and simultaneously we can see that when VD is 0, ID is 0, it reaches high value, then 0, then low value, and then comes back to 0. Okay, so this is ID max, ID minimum, and when ID equal to 0. So in this way, if we consider, okay, the Q point here for this point is over here. That is like, for example, let us just take, when you consider this point, okay, let me just change the color for this point and this point. When ID is max and VD is max, Q point is over here, and then we have ID is 0, VD is 0, and then it Q point shifts here, and later on it shifts here. So there is this particular Q point, it keeps on changing. Okay, so we can't take one particular point, or at a particular point we can't take what is VD and what is ID. Instead, we draw a tangent. Okay, and then we find delta ID and delta VD. Okay, so our AC or dynamic resistance is given by delta VD by delta ID. And one more approach is by using this particular formula, that is 26 millivolt divided by ID. Okay, there is some derivation after which we obtain this particular formula, and now we will not be discussing that. Okay, next what we have is average AC resistance. Okay, so if applied AC signal itself, okay, it has very large voltage swing, okay, then resistance offered by the diode, okay, is average AC resistance. Okay, and yeah, so what we do here is we connect, okay, two extreme point of the slope here and here. Okay, and after connecting the two extreme point, we basically obtain the slope. Okay, its inverse will give AC resistance or average AC resistance. Okay, and here basically we need to find the exact value, that is the points will be given. What is the V max value, what is V minimum, what is I max, what is I minimum, it will be given. You are supposed to substitute it and solve any problems related to average AC resistance. So next topic is about diode approximation. We basically have three different diode approximations. One is piecewise linear model, then what we have is simplified model, and then what we have is ideal model. So let's start with the most basic model, that is ideal model. Here we assume the diode to be a simple switch. Okay, I'll just try to Okay, switch in the sense when this particular diode is forward biased, okay, it acts as a closed switch. When it is reverse biased, it acts as an open switch. Okay, and basically it acts as a conductor with zero resistance in this particular case. Okay, and in reverse bias switch, it's basically open circuit which offers infinite resistance. This is an ideal model. Okay, and this is how its graph is shown. Okay, when it conducts current, a large amount of current flows instantly, and on the otherwise current is zero. Okay, next is the case of simplified model. Okay, this is the diagram of simplified model where we assume a voltage source connected in series with the diode. Okay, what it tries to show is that actually, as we already know and we have studied, even in case of case of forward biased condition, a voltage drop of 0.7 occurs. What it means is that when the applied voltage exceeds 0.7, large amount of current flows. Okay, now that concept is included in this case. What happens here is like as shown here, if in case of silicon it is 0.7, and for germanium it's 0.3, and that changes. Okay, that should be kept in mind. So in other words, when forward biased, 0.7 volt appears across the diode. Okay, and then what we have is piecewise linear model. Here, along with the voltage drop and switch, there is another concept of resistance. Okay, internal resistance or bulk resistance of the diode. Okay, and if we and as we can see here, this is one thing which I didn't specify about. As we can see here, until the barrier potential value, that is, let us assume 0.7 volt here, until that particular knee voltage the current is 0, and then it instantly raises to maximum value. Okay, and here in this particular case what happens is, along with potential and the switch, we even have resistor. So this is when you consider all the three models, this approximation is nearest to our actual diode working. Okay, where the diode is simply off until knee voltage. After that it increases slowly. Okay, and yeah, these are the three diode approximations. One thing that I forgot to specify is, usually this model, ideal model, is used to just check if the diode is conducting or not. In case of simplified model, okay, it's more accurate in the determination of load, current and voltage, and for the design of circuit and all, okay, we use piecewise linear model. Okay, that's all about today's session. Thank you.